Hi everyone, I hope you're well. Okay, so I'm going to go back through Newton's laws now as a bit of feedback. I had a lot of people telling me that they weren't sure, particularly about the second law, and amongst other things which I'll make other videos on. The way I want to do the next kind of two sections of lessons, so today and Wednesday, I would like to do, so that's an hour and a half each probably it's going to be. So 3 hours of kind of feedback over 2 lessons, and then we're going to move on with space for the remainder of the time until half term, and then we'll be moving on with chemistry after that. So thank you very much for doing that Google form for me. Nearly everybody did it, which is really great. And I've put a little feedback sheet of the main things that we're going to be covering over the next few today and Wednesday. On that, please read through that. Please make sure you learn the facts in the top right hand corner. They're really important. You need to know every single one of those. And I'm going to try and do kind of 5 minutes and maybe a bit longer on the second law maximum on each of the Newton's laws. So this video should be hopefully under 20 minutes long. So let's start. So Isaac Newton. Now we already know that he gives his name to the unit of force. So when we say, oh, we're measuring a force, it's blah-de-blah newtons. So it could be millinewtons, newtons, kilonewtons, meganewtons. We can put that kind of prefix in front of it again. But newtons is the unit whenever you do a force. And I just want to remind you that weight is a force, and I'm going to do a whole video on that because it is something that we clearly have not mastered. It was one of the most answered, is that the way of saying that, or one of the worst answers in the whole of that Google form. And the other thing about Newton it's very famous for, yes, there's the cannonball, I'm going to do a separate video on that, but are his 3 laws. Now 2 of the laws actually we've already done, we just didn't know we were doing them. So we've got, let's do the first law, really straightforward. What it says is, if there is no resultant overall force on an object, it is going to be either still or going at a constant speed. Exactly what we said before. What essentially it's that balanced forces, and then so no resultant force, no overall force, is equal to constant speed or stopped or stationary. That's all it means. Okay, so if we imagine we've kicked a football in space, it's going to look like that. There's not going to be any force diagrams on it, force lines on it, because we've already kicked it. It's left our foot, so there is no force acting on it anymore, because forces only act in the time they're actually touching. So as soon as that foot leaves the ball, no force, and it started to move. Now there is no air resistance, there is no friction, so there's nothing pushing back against it, and so therefore there's no force on it, but it continues to move in a straight line forever and ever until another force acts. Now that could be that it goes near a planet and the gravitational force acts on it. It could be that it hits something and so it experiences another force. But if it doesn't meet anything else and just carry on forever, this is how things like comets are moving through space. Okay, there's not someone pushing them along or an engine or anything. They keep moving forever and ever. They're thrown out of an explosion in a supernova when a star explodes, or possibly in the Big Bang, and they just start moving through space, and that's it. They keep going and going and going. Sometimes they get near planets, they might change their course because they're pulled on by the gravity of a planet, but they are not going to be changing speed. They're going to be going at a constant speed in a straight line. Now if you imagine this on Earth, if I kick the football, so let's say I've just kicked the football and the ground is there, it's going to start moving off in this direction. What we're going to see is that the friction from the ground and the air resistance start acting against it. So then we're going to get unbalanced forces, and we know that unbalanced forces means a change in speed, and so we're going to get to a point where the ball stops again. So you can't kick a football along the ground and expect it to go forever because opposing forces come out. But if you kicked it into the air, you're going to get air resistance, you're going to get the pull back down of gravity, so it's always going to be experiencing other forces. This law says that if it wasn't, then it would keep going forever in a straight line. If there was no friction, no air resistance. The only example of that is in space, really. Okay, you can't do it in a vacuum chamber because you're still going to have gravity pulling it down. So it needs to be out in space, nowhere near anything else, nowhere near any planets. Kick the football, off it goes forever. Okay, that's the idea. Let's look at the third law. I know I'm going in the wrong order, but the third law is also one that we have done before, but I just didn't call it the third law. So the third law states that every action has an equal and opposite reaction. What that really means is if one thing is pushing on something, like a book pushing on a table, then the other thing, the table, pushes back on the first thing. He uses the word bodies, so he's saying if one body exerts a force on another body, then the other body pushes back by the same amount. But essentially it's this, what we did right at the beginning of forces back in October. We had our book on the table. We said that it has balanced forces acting on it, so it's not moving. So the downwards force would be weight. Remember, weight is a force, so it's measured in newtons. And we said, okay, if that was the case, then this book is falling down towards the centre of the earth. It isn't doing that because the desk, bench, table pushes back on it by the same amount. I'll make that a bit bigger. Okay, and so we even called it the reaction force at the time. Reaction force, or R, also N, and these would be the same size, so 100 newtons, 100 newtons. Balance forces, first law, that means stopped or moving at constant speed, in this case stopped. That is Newton's third law, so it's exactly the stuff we've already done. I just didn't tell you it was Newton's third law at the time. Let's do another example. Let's imagine you're just stood on the floor. So here's somebody, it can be you, standing on the floor. You have a weight because you have a mass in kilograms, so you have a weight acting down. So we've got, let's say here, we've got, I don't know, what's an average person? An average adult is 750 newtons or 75 kilograms. So what that means is if you're pushing down on the earth with 750 newtons, then the earth is pushing back up with the same amount, 750 newtons. We call it R for reaction force. This obviously would be W for weight, and it's the same idea. Okay, balance forces, you're stood still on the earth. But what we're saying is what Newton's used the word bodies, and I talked about bodies the other day. In this one, body one is the table. The table, body one, is the table, the book. The book pushes down on the table. Body two, which is the table, pushes back on the book. You are, it doesn't really matter, body one, you're pushing down on the earth. The earth pushes back on you by the same amount. That is Newton's third law. And again, I bet you could draw these and tell me that they're balanced forces. You just didn't know that you were talking about Newton's third law. Okay, finally then, the more tricky of the three laws is Newton's second law. Okay, now this is the one that some people found quite difficult on the video. Okay, so it's maths. He says that the force acting on an object is equal to its mass times by the acceleration that it's moving. Okay, so, and it means resultant force really, so I'll put resultant here. Okay, mass times acceleration. So I'm going to use our car to demonstrate this. Just before I do that, I just want to talk about acceleration briefly. So I said acceleration is getting faster or slower by a certain distance per time. So meters per second, so that's a speed per second. Okay, now I also said that this is the same as meters per second squared, and I just want to demonstrate that to you with a tiny bit of maths. So I'm just going to use really simple numbers. So let's say you go 2 meters per 2 seconds. and per 2 seconds. So 2 divided by 2 divided by 2. Now 2 divided by 2 is 1, divided by 2 is a half. So this sum, if you put it into your calculator, this like that, should come out as 0.5 or a half. Now if you put this into your calculator, so we have 2 divided by 2 squared, which is the same as this one, so you're essentially doing 2 divided by 4, also comes out a half. So that proves to you that these are the same. Okay, we can do it with a bit more complicated numbers to prove it if you want. I might have to get my calculator here. So let's say we've got 20 for our m. S has to be the same, so divided by, I don't know, 5 divided by 5. Okay, that should come out as the same as 20 divided by 25, which is 5 squared. Okay, so let's try this and check. I don't know if you can see that. Where can I? It's because it's not on. There we go. Right, so the first one, 20 divided by 5 divided by 5, 20 divided by 5 divided by 5 equals 0.8. Okay, 20 divided by 25, 20 divided by 25 equals 0.8. Okay, so they are exactly the same thing. That is why we use this one, because it's actually a better and less messy mathematical way of writing this, but they mean the same thing. They are the same thing. You can see that with these numbers. Okay, so acceleration is how much your speed is changing over time. So how many meters per second are you increasing per second? So it could be 2 meters per second. That means you're getting faster by 2 meters per second every second. So in the first second you might be going 10, the next second you're going 12, the next second you're going 14, the next second you're going 16, etc., etc. That's what an acceleration is. It's a change in speed. If it comes out negative, it means that you're not actually getting faster, you're getting slower, but we would still in physics call it an acceleration. It would just be a negative acceleration. Or you can use the word deceleration if you want to. So let's imagine our car. Let's just do a toy car to make all the maths a bit less big numbers. So here's my toy car. Let's say it is, I don't know, 1 kilogram in mass. So if it's 1 kilogram in mass and it's the acceleration on the Earth is 10, it's got no wheels. We would then have a 10 Newton weight, sorry. And let's say it is moving along. I've got a 2 Newton force there, and 1 Newton force backwards, because it's moving along. It's going to have some air resistance, some friction. So the first thing I need to know is what is its resultant force, because actually I've got the force here and I've got the mass, which is going to be 10, no it's not, it's going to be 1 kilogram, but I haven't got the acceleration, so this should tell me how fast it's going. So my resultant force is 1, because I've got 2 this way and 1 that way, so my resultant force equals 1. My mass is 1 kilogram. This is going to be nice and easy, isn't it? So we've got, now I can rearrange this if I want to, because I'm actually trying to find acceleration here, aren't I? So I've got force equals F equals ma. I want to get acceleration on its own, so at the moment it's times by mass, so we need to divide mass on both sides. We've done this with Mr. Morkson, so that means that we've got F divided by m. We've got rid of m divided by m is 1, so there we go. So I need to do force divided by mass. So my force is 1 Newton and my mass is 1 kilogram, so very straightforward. 1 divided by 1. What this means is that my acceleration, if I keep this situation, I'm going to end up with my car going at 1 meter per second squared. Each second it gets faster by 1 meter per second. So it starts at 0, the next second it's going 1 meter per second, the next second it's going 2 meters per second, 3 meters per second, 4 meters per second, 5 meters per second, etc., until I get balanced forces. Now remember, balanced forces should mean constant speed. A constant speed should be no acceleration because it's not changing speed, it's constant. So you can prove this as well with this formula. So if we've got, let's imagine we get to a situation where we've got to a constant speed, so 2 newtons now. So now we've got 0, it's the same idea. We've got our acceleration, our force is 0, so we've got 0 divided by our mass, which is 1 kilogram, equals acceleration. Well, 0 divided by 1 is 0, so we're going 0 meters per second squared. So it doesn't mean we're stopped, it means that we're not changing speed. There's no increase in speed or decrease in speed. So it is simply a way of working out. You could work out the mass of something if you knew its acceleration and its force. You could work out the force, the resultant force on an object, a falling object or whatever it is, so long as you knew the mass and how fast it was going. So it's just using a formula and possibly rearranging it. I'm going to give you some questions to have a go at using this formula. And maybe a few force diagram questions on these. There's no need to be scared of Newton's laws. I know that I rushed through them the other day, but you already know the first law, you already know the third law, and you have done quite a lot of formula work already. So please try and get over that barrier, have a go at the questions, do your very best, and then once you've done those, watch the second video, which is Newton's canon. I think at the moment I haven't made it yet, I may change my mind on that, but I think it's going to be Newton's canon. Then you can have a bit of a go at doing some questions on that, and then hopefully we can move forward onto the kind of weight and mass bit, and some of the other stuff you got wrong or didn't understand last time. Okay, bye guys.